All right, in this lecture, I'm going to be covering the idea of node-based lists, which will be an improvement on our scheme-like int lists that we've seen so far. So let's start by grabbing those guys again from our Lecture 3 coding sesh. And now we have int list. How'd that file get here? Get out of here. Okay, so what I'm going to do is, well, let's take a peek at an int list. So as a reminder, an int list, as you guys have seen, has a head and a tail. And we use it as a way to store numbers, an arbitrary number of numbers. And if we want to use them, the code looks something like this. So let's just make an int list launcher, demo of int list ops. And what we'll do then is maybe create an int list called L, or how about X? New int list 100 null. So that's an int list containing the number 100. Now I might do, say, x.tail equals new int list 100. Well, it's not a very exciting number, 5 null. And so after I've done those operations, well, what do we expect the int list x to be? Well, it should be 100 pointing at 5. Okay. So at this point, that is what x is. Okay. So fair enough. A little awkward to use. I mean, like the syntax is not totally 100% clear. We have to think about what variables you're doing. That's not the end of the world. Okay, well now let's see where we run into some funny issues. Let's say we say int list y equals x. So in that case, after that line runs, we also have that y represents this int list right here. So a question I asked in live lecture was, how do we add to the front? So how do we add to the front of x instead of to the end? So if you'd like, you can pause now and figure it out. If not, here's the solution. So what I'm going to do is take x and say x is actually going to be a new int list where the front, let's say we're adding the number 99. So we do x equals new int list 99 comma x. After we've done that, we have the situation that x is 99 pointing at 100 pointing at 5. What's y? Well, it hasn't changed. It's still 100, right? It's if we think about this, really what it is that y is pointing at an int list which contains 100 as its head and this over here as its tail. So y has not changed. Okay, and if you're not sure about why that is, definitely play around with maybe the visualizer and make sure that makes sense. All right, but here we say that this is a funny feature. So it's just inconvenient. I mean, as Java experts now, well, we're getting there. We can parse this out and feel good about it and say, okay, of course that is. But it's an annoying fact, right? I mean, just like casually reading the code, y equals x, I change x up a little bit. Like if I add to the front of x, suddenly they're not equal. Like that's just an inconvenient feature for a data structure. So that's one problem. Another is that there's no way for us to represent an empty list. So that's a very natural idea. If you've used Python or MATLAB or Scheme, you know that there's this idea that we can have an empty container that we can start adding stuff to. And that's a lovely thing to be able to do. It's very handy. But in Java, with what we have so far with these scheme-like int lists, let's say we wanted to create an empty list. Well, the most natural choice, well, if we do new int list, I mean, this is certainly not an empty list, right? Whatever we put here, it's in the list. So the closest we could do is say null. But then the problem is if we were to say, I want to print out the size of this null list, then if we run it, we'll see if there's other bugs here. We get null pointer exception right here because of the fact that x is actually null. So we can't ask for the size of a null thing. No matter what code we put in here, we can't say like if this equals null. That doesn't make sense. Not allowed in Java. Okay, so that's the crux of the issue that we're going to try and solve. And so what we're going to do is make things a little better. To face those challenges, we're going to do a silly little thing. It's going to seem like we're doing nothing at all. We're going to start by rebranding an int list and giving it some new names. All right. So what I'm going to do is take int list and I'm just going to rename a bunch of stuff. Okay. So notice these are the difference between an int list and an int node. Okay. Now notice there's only two differences. One, there's a name change, and two, where we used to have ... here, all the various things that int lists can do. Now I'm just saying, nope, sorry, not allowed to add any more stuff. Okay. So in other words, here's int list, I'm going to now turn it into int node. And why we're doing this will become apparent. So as I said, I'm going to cut all this stuff out. And then I'm going to say, you know what, int list, you are now called int node. So I guess we'll even be fancy and we'll do a find replace. Oops. Or will we? Okay, int node. Okay, done. Head, well, this is going to now be called item. This will be called item. This will be called next. This will be called next. This will be called in. And this will be called in. And this instead is going to be, well, I guess it still defines a recursive integer list. Yeah, that's fair enough. It does. Okay. So now we have int node. And that's going to be the key component for what we're going to do next. All right. So what we're going to do is create a class called SList. Uh-oh. What is this? SList. Oh, I'm in the wrong folder. Ignore that. Okay. So what I'm going to do is SList.java. And this is going to be a much more user-friendly and reasonable list of class representing a list of numbers. Okay, but we're not going to write any of the code here yet. We are actually going to start with SList launcher. So I'm going to lay out what our goal is by talking about how using an SList should work. Okay, so it's a good idea to get a sense of where we're going before we start trying to build it. So it demonstrates the power and elegance of the SList. It's a fine class. I don't really need a comment here. Okay, so what we're going to do is just take int list launcher and translate, because we want it to do the same thing as an int list, but just less uglily. So I'm going to start by saying that instead of thinking about null, what an SList is going to do, and I'm going to make SList, yeah, x, new SList, and for this call, I'm just going to make it do 100. Okay, so that's going to be our most basic thing. We can create an SList with 100, and we're not going to be thinking about the nulls as a programmer. Next, what I'm going to do is say x.insert back, and then we'll put in the number we want to insert, and then our goal is that x should represent this. Okay, when I do slist y equals x, then y should be equal to this. In this case, well, actually, no, I won't say anything about that yet. Okay, so now when we add to the front of x, it's going to be slist, or it's going to be x.insert front 99. And now we'll have the nice feature that this is 99, 105. So this is the new behavior, which is what we want, right? We found it awkward that this happens, so we're going to do this instead. And then finally, we're going to be able to say x equals new slist nothing, and still be able to print out its size. Okay, so that's our goal. This is what we want to build. Let's start filling in our slist class now, so that this stuff all works. So if we look at SList launcher, we see that the first thing we're able to do is instantiate an SList with a number. Okay. So what I'm going to do then is, well, I guess that means I need a constructor, public SList and x, and I need to take this number and put it somewhere useful that we can get it back later. Okay. And somehow I'm going to be using int nodes. So the natural thing maybe is I'm going to create a new int node called that takes in the number x as one of its values, and I'm going to use and say its next is null. Now it's not an obvious 100% choice, but seems like a good start. So I say new int node x comma null, and now I want to take this information, put it somewhere that it can actually stay. Because if I run this code, right, if this were the constructor, it would create an int node, and then we wouldn't save it anywhere, and it'd be lost. So I'm going to say, let's create a variable. I'm going to call it front for reasons that will become clear later. And we'll say front equals new node int node x.null. Okay, and so this right here will allow us to save this 100. So I'm actually going to comment out some lines because these things aren't implemented yet. And I am going to now see if this works. Okay, so we run this and everything compiles. So now we want to see if this number is here. Well, how do we do that? So exercise for the reader. What would you print in order to see if that 100 is there? So you might pause or not. So let's say we do x dot front. So x is an slist. If we do x dot front, what do we get back? Okay. Oh, well, we get this strange thing. What is that? Well, that's saying that you're trying to print out an int node, but an int node isn't like a number, so you get whatever this thing means. And so we need to get the contents of the int node. There's an item inside. So to get that item that's inside that int node, we run this, and we get 100. Okay, great. All right, next let's implement insert back. So we say public void insert back. So it doesn't seem to return anything, and it takes an integer. And now we're going to make sure that it ends up at the back of the list. Okay, well, what is an SList really? Well, it seems to have an int node, and this thing, as we know already from int lists, this is a good way to represent numbers as a scheme-like list, so we'll just stick it at the end of this list. So we haven't written insert back before with int nodes, but the pattern is going to be pretty similar to something we've seen. So I'm going to create a pointer. And again, not a bad exercise to try and figure out what I'm about to do, so you might pause and think about this. But I'm going to say int list p equals front. And I want to step p along until p dot next equals null. Because this means that that p is the last item. Okay? So we want to get p so it's pointing at the last item. So let's try that out. Okay, so while p dot next not equal to null, p equals p dot next, and then finally, I guess I'll put this comment up here. So now we know that p is the last item. So if p is pointing at the very last thing at the list, well, then the natural thing to do is to say p dot next equals new int node x null. Okay, so we're taking this thing and sticking it at the end, and now hopefully it should work. This is our goal. We want this to be 100-5. Okay. If we think about what we just did, before we ran this command, x was 5. So we got it so that p was pointing at this, well, maybe I'll put a little box around it. So this is an int node. So we said, hey, int node, make it so that your next is a new int node. Let's see, back. Sorry, this is what we had before. So we had 100. We found the end of the list, and then we said, last thing in the list, your next is a new int node. Okay, so let's see if that worked. So what we're going to do is do system out println, and again, x.front will give us this box. If we do x.front.next, we get this box. So if we print it now, we're printing out something of type int node, and we get, there's a bug. Int list p, int list. Int node. Okay, so now we get this thing at the front, or we get this box. Now, I mean, it's not obvious from this that this is that box, but if we look inside, we should hopefully see a 5. Okay, good. All right, so that's insert back. Okay, next up comes SList y equals x. Do we need to do anything in SList to make this work? Do we need to like define equals? No, not at all. As we said in lecture 4, maybe 3, I don't remember, the equal sign means exactly one thing. It means take the contents of this simple container and put them in this simple container. Yeah, that was lecture 3. That's it. That's all equals ever means. And if you're not totally convinced that this works, then that means you are not totally comprehending exactly what equals is supposed to do. But I mean, if we run this, there should be no surprises here. So we get 5 again, right? Just like we had here. Okay, so y and x point at the exact same thing. All right. Next comes insert front. So let's do public void insert front int x. And now we'll find that this is not such a tricky method to write. So to do this, what we will do, well, let's look at our int node, our int list for int list launcher for inspiration. So this is how we stuck something at the front of x when it was an int list. Now we want to insert something at the front of this this right here, this int node, which basically is just an int list. So if you have not paused to consider what I'm going to do next, I really want you to pause this one and make sure you get it. Okay, you might even draw out a little diagram. Okay, so give it a shot. If you get stuck, that's fine. You can unpause and find the answer, which is what we want to do is say that the front node is equal to new int node front x, precisely mirroring what we had with int lists. So here is int list. All right, this is how we did it with int list, and this is how we do it with SLists. Yeah. And then we don't return anything. And that should work. At this point, what we expect is that both x and y look like this. So let's do a little test here and see if that works. So we'll have x dot front dot item should be 99. Okay, front equals new int node front x. Oh, I had the things backwards. Okay, so maybe you caught my bug. You couldn't shout me down to fix me. Yeah, so I had these backwards, sorry. Okay, so we get 99, just as we expected. So this is what we expected to be there. And of course, since x and y are pointing at the exact same SList object, it should work now. We do this. Okay, so we're both 99. So let's look at that visually and see what this means. So if you've been a little shaky about this, I hope this will help elucidate what's going on here. So we've created this class called SList. It has roughly these methods that we have not actually written this getFront yet. We've also done insert back. So this is the picture. This is what a scheme-like int list looks like up here. So whenever I create a variable, so if I have a variable of type int list called x, it's a simple container which has this arrow inside and points at this whole object here. And then if I had another one called y that pointed here, it would be pointing at I guess this, we'll think of this as a sublist, all right? So this whole thing is a scheme, or this thing is a scheme-like list where each list consists of a head and another scheme-like list. Okay, now our new scheme, which is the much more Java-y way of doing things, is to say, I'm not going to let anybody point at the underlying recursive data structure. I mean, it is nonetheless an int list, no question. But what I'm going to do instead is I have this right here, this thing called SList that has a set of methods, insert front, insert back. We haven't done getFront. And so if I point at an SList object, then it's an intermediary, right? So it doesn't matter, like, we don't have this weird problem where adding to the front makes x and y get out of lockstep because x and y are pointing at this thing. It's like a container, right? So makes our lives easier, right? I mean, you can just see it. Compare SList launcher to int list launcher. Modulo all the print statements. This is awkward to use, right? This is easy to use. X equals new int list, x dot insert back. So that's the fundamental idea we have now with SLists. It'll make our life cool and great and wonderful for various reasons we will soon see.